Okay, we're back for section 2.2 of geometry. We're going to be talking about a biconditional in this section. A biconditional is a statement that it's called an if and only if statement. It's if a conditional and its converse are both true, then you can combine them into this if and only if statement. One thing that sometimes, in order to avoid writing if and only if over and over, sometimes people will write IFF, the two F's. It looks like you've misspelled it, but it really stands for if and only if. So if you see me write that, that's what I'm meaning. And also, if I'm using my P and Q representations, I would have an error that had two ends to it, because if P then Q and if Q then P. You're taking the conditional and its converse and you're putting them together and saying it's true either way. Both the conditional and its converse are true. So here's an example. If two angles have the same measure, then the angles are congruent. That's the conditional. The converse is if two angles are congruent, then they have the same measure. Now, if I went and checked these two, if I looked at them and tried to think of counterexamples, it turns out that the conditional and its converse are both true. So that means I can write a biconditional, and I would say I'm going to put them together. Let me just look at these two things. In the first example, the conditional, the hypothesis is two angles have the same measure, and the conclusion is the angles are congruent. That was my P for the hypothesis and the Q for the conclusion. And when the converse switched those and said if two angles are congruent, then they have the same measure. So what I'm going to do is, I can really pick either one, but I'm going to go with the conditional, and I'm not going to write the if in front. I'm going to say two angles, starting with the hypothesis, two angles are congruent, or two angles have the same measure. If and only if. So I'm using my shorthand with the I with two F's. If and only if the angles are congruent. Now notice I didn't have an if and a then. I had if and only if. That goes in the middle and not at the beginning where the if usually goes. I also could have written this the other way around because they're true either way. So I could have written if two angles are congruent, or not with the if in the front. Two angles are congruent if and only if they have the same measure. So I could have written it with either the hypothesis or the conclusion in the front. No if in the front, and the if and only if goes in the middle. So there's not a then either. Okay, now I want you to look at the next one. I want you to look at if x equals 5, then x plus 15 equals 20. I want you to write the converse, and then if both the truth values are true, then I want you to write the biconditional. So pause and do that. Okay, x equals 5 is my hypothesis this time. X plus 15 equals 20 is my conclusion. So when I write my converse, I will say if x plus 15 equals 20, then x equals 5. Okay, it turns out that both the conditional and its converse are true, so I can write a biconditional. And it doesn't matter which one I put first, but I'm going to use the conditional, so I'm going to say x equals 5 if and only if x plus 15 equals 20. Okay, so my if and only if is in the middle. All right, now, sometimes we're going to start with a biconditional, and we need to separate it into parts. So here I have a biconditional that's written already. A number is divisible by 3 if and only if the sum of its digits is divisible by 3. This is one of the rules of divisibility that sometimes will help you to reduce things. So something that you learn in arithmetic, but it is a true statement. It's a true biconditional. And so what I want to do is separate it into its parts. So remember, when we just wrote them, we usually put either the hypothesis or the conclusion first, before the if and only if, and then we put the other after the if and only if. So I'm just going to call the first part the P, the second part the Q. And now I can break it into its conditional, because the conditional, remember, is P implies Q, or if P then Q. So I would say if a number is divisible by 3, I'm using shorthand. Then the sum of its digits is divisible by 3. Oops. Okay, that was the conditional. The converse will put the Q first. So if the sum of a number's digits is divisible by 3, then the number is divisible by 3. Okay, so that's how we separate it into a conditional and its converse. Now I want you to look at the next example. Lines are skew if and only if they are non-coplanar, and I want you to break that into its conditional and its converse. You should be pausing to try to get the answer on your own and then coming back to check. Okay, so on this example, the lines are skew, I marked as P, the hypothesis, and they are non-coplanar, I marked as Q. So it's the part that comes before the if, and the if and only if, and the part that comes after it. For the conditional, I made it say if lines are skewed and they are non-coplanar. For the converse, I will just switch the P and Q around. So I'll say if lines are non-coplanar, then they are skew. Okay. So one of the things that we use biconditionals for is to write definitions. And so we need to know what makes a good definition. This is also something, if you've taken logic, you've probably seen in logic. There are three things that we need to check. One, that's using clearly understood terms. That means things that people commonly understand, and it could also include terms that we've defined previously. So if we were using geometry words, then it might not be terms that people understood clearly commonly, people who hadn't taken geometry. But if it's in geometry in Chapter 2, then I'm assuming I can use any of the words that I've already defined in Chapter 1, and so on. Okay, and then the second thing we need to check is that it's precise. So I'm not going to use words like big, large, sort of, almost. I want to be really clear and specific. And the third one is that it's reversible. So if I can write it as a true biconditional, that means I can write the conditional out, I can write the converse, and both of those are true, and so that means I could make it into a biconditional statement, then that makes a good definition. So let's check one. Let's check a definition. Here we have perpendicular lines are two lines that intersect to form right angles. Okay, so I'm going to try to make a conditional out of that. The first part I'm going to use as my hypothesis is the first part of the definition. So I'm going to say if two lines are perpendicular, right, and then the second part of the definition I'll be using as my conclusion. So perpendicular lines are two lines that intersect to form right angles. So if two lines are perpendicular, then they intersect to form right angles. So I've just used the purple as the hypothesis and the blue as the conclusion. All right, that is true. There's not a counterexample that shows that there's a time when the hypothesis is true and the conclusion is not. Okay, the converse, I'll just switch those around and say if two lines intersect to form right angles, then they are perpendicular. That also is true. There's not a time when two lines intersect to form right angles, they are not perpendicular. So there's no counterexample for that. All right, so since both of those are true, I can put them together into a biconditional, and I can say two lines are perpendicular if and only if they intersect to form right angles. So if I can take a definition and I can make a conditional and a converse that are true, then I can combine it into a biconditional, and that says that it's a good definition. All right, so let's try that. Sometimes we are trying to show that a definition is not a good definition. So here I've got, number one, an airplane is a vehicle that flies. So I want to think about that, and I want to see if I can break it into make a conditional out of it. So I might say something like, if a vehicle is an airplane, or let me make it even more generic here. If something is an airplane, then it is a vehicle that flies. Okay, that is true. That's the conditional. Now let's see if we can reverse it. Let's say we reverse it and we put, if something is a vehicle that flies, then it is an airplane. Is that true? Okay, that is not true. The reason is I can come up with a counterexample. A helicopter would be a good counterexample of this. So in this case, the reverse was not true. It's not reversible, which makes it not a good definition. Okay, so that's the end of section 2.2. Go and try your problems, and we'll go over any questions you have on Thursday, or you can shoot me a text if you're having any trouble before that.